to think about now are functions where we can calculate the gradient, or the gradient of R of W, but can't on paper solve for where the gradient is 0. That is the type of function I want us to think about now. Okay? One where the gradient exists, you can find it, you can write it down on paper, but you can't solve for where it is equal to 0. What is such a function? Let's just take, for example, did you have a question?
No.
Okay. Let's just take, for example, this scalar to scalar function, f of x. It is a 4th degree polynomial. Okay? It has a minimizer. It's somewhere over here. But remember, whatever we develop shouldn't require looking at a function, because computers don't have eyes, right? And if we're dealing with a vector to scalar function with millions of input variables, as we are in practice, you can't just look at it and know where the minimizer is. Okay? But we know this one has a minimizer. But if we try to use a gradient-based approach, like take the gradient of it and set it equal to 0, which in this case would just be taking the scalar derivative and setting that to 0, what would we end up with? What is the derivative of this? Yeah.
20x cubed
20x cubed
bx squared
minus 3x squared
is 10x plus
2. This is a degree 3 polynomial. Okay, and there's no really efficient way to solve for roots of a degree 3 polynomial on paper. There actually is, like, how there's a quadratic formula for roots of degree 2 polynomials? There is a complicated degree 3 formula and an even more complicated degree 4 formula. But there have been proofs by famous mathematicians that for degree 5 polynomials and beyond, there is no formula for where those polynomials are equal to 0, unless they're very special cases like they factor nicely. So there is no degree 5 equivalent of the quadratic equation. So our gradient-based approach of taking the gradient and setting it equal to 0 won't always work. When we run into sufficiently complicated functions, you can calculate the gradient, but seeing where it's equal to 0 on paper may not work. And so instead, we might think about, what does the gradient tell us conceptually about a function at a point? And so in this function's example, again, this is not a gradient, it is a derivative because it is a scalar to scalar function. What does its derivative at a point tell us? Like if I plug in here and figure out that its derivative here, I don't know, what is this input? Negative 1.2 is equal to negative 6. What does the derivative here at a point tell me? Okay.
decreases.
Yeah, it's telling me that at this very specific point, the function is decreasing. Whereas here, the derivative would tell me the function is increasing. Okay? So I want us to reframe our mindset. Instead of trying to solve directly where the derivative or gradient is equal to 0, why don't we just assume we have this black box that tells us what the gradient of the function is at any point, but we don't have a way of figuring out exactly where it's equal to 0. What I want us to do is come up with a guessing game to try and figure out how to make the gradient as close to 0 as possible. Okay? Suppose all you know is that at the number you plugged in, the gradient is positive. Okay, let me stop interchanging gradient and derivative. Let's just work with this example here. I plug in a number into this function, and it tells me at that number the derivative is positive. And my goal is to try and find where the the derivative is 0. What should I do? If at this point the derivative is positive, what should I do? Mark?
The opposite direction?
Yeah, I should decrease the input. Because the fact that the derivative here is positive means if I move to the right, the output will go up. If I'm trying to get to the bottom where the derivative is 0, that means I should move to the left or decrease my output or decrease my input. Do you agree with that? So I'm going opposite the direction of the derivative. What about here? I plug a number into this black box and it tells me there the derivative is negative. So what should I change about the number I plug into the black box? Should I increase it or decrease it? What should I do?
Increase?
Increase, yeah, because if the derivative is negative, that's telling me if I keep going in that direction, the output's going to get lower. All right? So even though in this hypothetical you can't look at the function and you can't look at the formula for its derivative, knowing the derivative at a point tells you something about where the minimum is relative to that point. If the derivative is positive, the minimum is probably to the left. If the derivative is negative, the minimum is probably to the right. Okay? How does all of that change when we look at, I'll let this load here, functions with multiple input variables? Because now the derivative doesn't just have a sign, but its gradient has a direction. Let's let this load here. We recall from last lecture the idea of a contour plot, right? As a recap, imagine this is a function. It is a vector to scalar function with two input variables. And my goal is to try and use the gradient to estimate where the function is minimized. If I look at it through this bird's eye view, it might look like this. And the gradient, when I plug in any input, tells me what? What does the gradient when I plug in any input tell me? Yeah.
Which direction the function is increasing the fastest.
Yeah, it tells me the direction along which the function is increasing the quickest. But in this thought experiment, what I want to do is try and find where the function is minimized. So if at this point it tells me if what you want to do is climb up the curve the quickest, go in that direction, what should I, in what direction should I start looking if I want to get to the bottom as quick as possible? Yeah.
Negative.
Yeah, the negative of that. Okay, if it tells me pointing in this direction gets me up the curve the quickest, well then I should point in this direction and start looking there. Do we agree? Okay, so that is the essence of the gradient descent algorithm. It is an iterative algorithm where all you're really doing is just updating your guess for where you think the bottom of the curve is. And you update it by walking in the direction of the gradient at your current guess. Because at your current guess, walking opposite the direction of the gradient. Because at your current guess, the gradient tells you how to increase, so you just walk the opposite way if what you want to do is decrease. Okay, that is the essence of the algorithm. Okay, I'll show you some visual examples, and we can formalize the sort of math for the algorithm when we come back on Wednesday, but I just want you to have the intuition here. Let's start with this scalar to scalar example. With gradient descent, there are two aspects of the algorithm you need to pick ahead of time. First, you need to pick where you're going to start your guessing, your initial guess. Then you need to pick how much you are going to travel in the direction of the gradient. That's called your step size. So here, I've said, hey, let's start my estimation by starting off with x equals 0, and my step size is going to be 0.01. So whatever the derivative is at that point, I'm going to move 0.01 units opposite the derivative. Okay? And when I start, you can play around with this in the notes as well, what happens? And remember, the algorithm doesn't have eyes, so it doesn't get to see that it did this correctly. But what happens? It finds the minimum, right? It finds the minimizer. It inches along there, but it gets there. But right away, you can see that this doesn't always work, because if we started our initial guess up over here, it gets trapped in a local minimum. So the existence of a local minimum kind of fools this plan, right? Because this plan really is just centered around finding where the gradient is 0. But if a function has local minima, well, then the gradient could be 0 at multiple points. That's not the only possible outcome. You could also pick a step size that is too big. It's kind of glitching here. But your algorithm doesn't necessarily need to converge if you make too big of steps in the direction of the gradient. What does this look like in 3D or for a vector to scalar function? Well, note that here around negative 1, comma 0 is the true global minimum. Depending on where you start the algorithm, you may or may not actually converge at the true global minimum. Here, we got trapped in a local minimum, okay? And you can see at each of these steps, the direction is changing, because as we update our guesses, the direction of the gradient changes, and so the direction of the negative gradient also changes. So the angle is changing as we move along the algorithm. Here, we started with a different initial guess, and you can see the direction happens to point us to the right place, which is the true global minimum. But again, if you pick a step size that is a multiplier on the gradient that is too big, well then you may just end up bouncing circles around the minimum, but not actually converging. So these are all things that could happen. And just so you see it here today, this is the algorithm for gradient descent. It's iterative. It says your new guess equals your old guess minus this step size thing I just told you about times the gradient at the old guess. And you just use this to update your guesses. And all of the visuals we just saw used this. So gradient descent is the last big idea that will be on midterm 2. And when we come back on Wednesday, a lot of what we will do is just focus on understanding how gradient descent works and what could go wrong. But a good activity to work on, perhaps, and the type of question you might see is one like this, which is activity 1